The Center for Nanophase Material Sciences is a scientific user facility, and it's our mission to develop some of the best instruments in the world that are unique for looking at nanomaterials and understanding phenomena at the nanoscale.
My job is using a scanning tunneling microscope to look at the materials in the atomic scale. So with this microscope, we can see the individual atoms in the materials, and also we can see their quantum properties. And by using that, we can figure out what's the great part, what's the quantum phenomena we can find out from these materials.
Specifically with regard to electron microscopes, we can use the sharply focused atomic beam to energize the material, so we can actually pick a specific atom, can put a large amount of energy into it. That can sometimes cause it to leave the surface, and then we can have another atom come in and dope it.
So I work at the intersection of physics and machine learning. We call it physics-based machine learning, and the reason we need it is that we cannot just take the already available machine learning models developed by Google or Facebook and apply them right away to our scientific data, because those models trained on things like images of cats and dogs on the internet, they're not constrained by physics. They usually do not allow incorporation of prior knowledge. The first step is that we analyze scientific data and we look for patterns in the data, and the second step is that we use this information to actually guide our measurements. As far as applications of machine learning in materials and atomic manipulations are concerned, first, we can acquire really huge amounts of data. And then the question is how we're going to analyze this data. And manual analysis may not necessarily work. It's not very efficient. And this is where machine learning comes into play, because we want to find patterns quickly.
Majorana quasiparticles are very exotic particles that in a solid can emerge from collective states from electrons. But very different from electrons, they are actually their own antiparticles. And even more exotically, they are what we call non-abelian anyons. And that means that if you take two of them, and you exchange them twice to get back to the initial state, you actually get back to a very different state. If you have several Majoranas and you exchange those, the final state even depends on the order of the exchange operation. And it turns out that that property makes them extremely useful for quantum computation. In solid-state systems, Majoranas can be created at the boundary of very exotic materials. So just like the particles themselves, the materials have to be very exotic. They are what we call topological superconductors, and because they are so exotic, they're very hard to find in nature. But it turns out that one can actually engineer these systems using artificial hybrid structures. One way to realize that, for example, is to grow a one-dimensional atom chain on top of a superconducting substrate. So then you will have Majorana fermions located at the end of that chain. My work with computation and modeling of Majorana quasiparticle systems involves mostly large-scale computing. It involves quantum many-body theory for microscopic model Hamiltonians.
What makes the work we do fairly unique, first of all, we have some of the best microscopes anywhere. We've built feedback and control schemes that allow us to very controllably modify materials at the atomic scale. This is important, first of all, because it allows us to do our research that we're interested in doing on quantum materials, but we also make this capability available to users from around the world.
We have a very specialized and unique state-of-the-art STMs. One is this 4-probe STM, which has 4 STM scanners that you can operate independently. So you can do the scanning with all these 4 probes, get the atomic resolution images and do the electronic properties. But also you can do the transport measurement, so see how electron flows from one probe to the other probe. You can get these transport properties of the materials by using this 4-probe STM all the way down to the atomic scale. So you can see the atomic scale transport, which is very unique capability of this 4-probe STM.
At Oak Ridge, we've got quite a few efforts in the quantum direction. We're the home of the Quantum Science Center, which is a large multi-institution collaborative effort to study topological materials. And then next to that, we have some of the best material scientists anywhere. We've got the ability with our clean room to modify these materials. We've got excellent theory and one of the biggest supercomputers in the world for predicting how these materials behave.